Welcome to the Control Engineering webcast, Demystifying Servo Sizing, sponsored by Yaskawa. I'm your moderator, Mark Hosky, and I'm happy to join you today on behalf of Control Engineering. Here are some tips to help you get the most from today's webcast. If you're experiencing issues with your slides or audio, please refresh your browser or click the Refresh Media button directly under the presenter's picture. You can control the volume of the webcast by adjusting the volume on the computer or by adjusting the volume on the webcast platform. If you're having technical problems with audio or the slide presentation, click on the question mark at the top right corner of your screen to access a list of system checks to try before contacting an online technician. But if you do need a technician, type a message in the Ask a Question box and someone will get to you as quickly as possible. Type the questions for our speakers in the Ask a Question box on the left side of your screen. The live Q&A session will begin after the presentation concludes. Today's webcast is being recorded. You will receive an email within a week with the link to the on-demand event. To download a certificate of completion and a PDF copy of the presentation, use the Event Resources tab on the left side of the screen. Those documents also will be available with the on-demand version of this webcast. Now we will hear from the sponsor of today's webcast, Yaskawa. At the conclusion of the video, you may experience a few seconds of silence to compensate for varied internet speeds. Please stay tuned after the video for today's presentation.
Hi guys. If you've ever been tasked with sizing servo motors for motion control systems, whether they be retrofits or brand new design machines, never been done before, there are certain key questions that you want to ask and have an understanding about. This webinar is going to cover those questions that you want to ask your customer or just have a general better understanding before you start going through the sizing process. That's all coming up, as well as sizing software that'll ease that transition. Again, it's all coming up live here next in a couple of moments. Tune in. Thanks.
I'm happy to introduce today's presenter, Sixto Morales. As Senior Regional Motion Engineer, Sixto Morales has spent more than 10 years working in motion control for Yaskawa America Incorporated. His diversified, worldwide experience comes from time invested in the field. He holds a bachelor's degree in electrical engineering from DeVry University in Irving, Texas. Thank you for joining us today, Sixto. I'll hand it over to you.
Hey, thanks, Mark. Appreciate the introduction there. As Mark said, my name is Sixto Morales. I lead up the Southwest Territory for Yaskawa in the Regional Motion Engineering Department, as well as Latin America Sales Manager. Now, imagine, if you will, that you are on a plant floor and the machine that you've been working on for a while now is kind of nearing end of life, or there are parts of this machine that are just constantly breaking down. And you know that you've got to upgrade some time, or you've got to do some sort of sizing to know what motors fit on this particular machine. What do? Well, today's webinar is going to focus on just that. So why are you listening to this webinar? The main purpose is going to be to give tribal knowledge of how to size servo motors for typical and various applications, and to be able to use those concepts in multiple different areas of sizing. To do that, we'll follow a process where we're going to go through some common mistakes, some of the do's and don'ts of things that you should or should not do. We're also going to look at some example servo applications, the various different types of servo motors that Yaskawa has to offer. We also want to look at the importance of gearbox selecting, specifically a certain series of product that you can use. And we will wrap it all up with some live sizing. We'll do an application together where we will demonstrate the software to go through. In the end, the payoff is you will be able to appreciate the servo sizing concepts and make an investment comparison. And hey, in the end, you'll be able to say, I am awesome. Well, not me, but you. It's got to be your bull, right? You are awesome. You'll be the hero. So let's look at, do you have any sort of these applications in your plant? Perhaps there are some bottling or labeling applications that you have, or there may be some R&D or gantry systems that you're looking at as well. There could be some sort of a spindle or traverse machines that you're working on. Getting a little bit more complex, this application is a slitter or a sheeter application. You could also get really, really crazy with it with a whole bunch of pulleys. In this case, you've got quite a bit of pulleys in there for the various servos that are in there. And let's get really huge. Let's look at some hexapod applications. So at this point, if you wouldn't mind, there is a chat area where we can start to look at the poll questions and see what kind of various applications do you guys have in your plant. So while we wait for those to come in, we're asking which type do you have. There are numerous other applications that we didn't really touch on so far, just looking at those. But from what we see right now, there are, wow, this live poll is pretty cool. So we're seeing a lot of the gantry applications that are coming in. Oh, now actuators are filling in here. This is pretty neat. Pulleys are running in third place right now. So we see that most of these applications, okay, so actuators, we've got some pulleys, and we've got some gantry systems out there. This is pretty cool. Thank you, everyone, for being able to write and type in there for the various applications. So it's interesting and really neat. I believe that this presentation will help in determining the sizing that we will go through. So back to our slides here. So what presentation wouldn't be complete without a little bit of marketing? By the numbers, Yaskawa is a $4.5 billion global sales company. We've been in business over 100 years, ever since 1915. We have sold a ton of servo amplifiers, variable frequency drives, huge robots. We employ over 14,000 employees, and we are in 30 countries with Yaskawa sales and service and manufacturing locations as well. That was my one slide for marketing. Don't worry. Let's move on to some common mistakes that we have seen in the past for sizing. So we'll touch on this one. The mistake number one is using an AC induction motor versus a servo motor. In this case, the AC induction motor is usually identified by horsepower. It needs a variable frequency drive or a starter, and it's current driven. But there are some things that it does not have. It doesn't have any internal feedback or knowing where the position is, no precision, and it does not have any sort of torque control. It does make for a smaller investment. You could go out and purchase an AC motor into your application, and just about any hardware store would be able to have that. On the other hand, when we look at servo motors, they are identified by kilowatt, which isn't really that different from horsepower. It's just multiplying it by 746 watts. It does need a servo amplifier. The servo amplifier will be coupled with the servo motor, but the servo motor does have internal feedback. It does have precision, and it is a larger investment for an application. So mistake number one is that you can't always use an AC induction motor in place of a servo motor. Well, let's continue on with this. So if we remember from Ohm's law, P equals I times E, or pi, you can notice that the internals of the motor, particularly for an AC induction motor, it converts electrical energy to rotational energy. And by doing that, you've got the internals of the rotor, which are going to be put into the motor, and then it's going to be wound around by the wound stator. And how this happens is it is current driven, so you induce current, thereby creating an electrical field. The rotor will continue to always chase that stator, and the lag in that chase is what's known as slip. It won't really ever be synchronous, but that is the internals of how a motor will be able to convert electrical energy to rotational energy. So moving forward, what is a rotary servo motor? Well, a rotary servo motor does also have, it uses electrical energy into rotational motion, but it's handled a little differently. It does provide speed, usually put in revolutions per minute or RPM. It does provide torque, can be in Newton meters or pound feet, and it does have position feedback. The rotor, in this case, is made up of laminations or permanent magnets, kind of put all together, then magnetized. These are neodymium iron boron magnets. The stator is wound with copper windings all around through the housing of the motor. And voila, you get a nice servo motor. But the one thing that this does have internal is the encoder. The encoder is put at the back of the motor. And this particular series uses Sigma 7, which is a 24-bit encoder. The number is over 16 million pulses per revolution. Very, very precise. Let's move a little bit farther into a linear servo motor. It also converts electrical energy, but this case, it's going to be converting it into linear motion. It is made up of a magnetic way. It provides speed, either in meters per second. It does also apply a force. And the position feedback comes in from a linear tape scale that's laid on the side of the, in this case, the Sigma Track 2 or the linear motor. It'll provide the resolution, the feedback where that carriage is. The moving coil moves basically back and forth. If you were to take the stator that we had from the rotary, cut it in half and open it all the way, you would have the magnetic way, and the moving coil would be riding on top of that. So an AC induction motor does not always go hand in hand with a servo motor for our various applications. That's mistake number one. When we switch looking at mistake number two, ignoring inertia ratio is also another big one. And typically, there is plenty of torque, there's plenty of speed for the application, but one thing that's missing is the inertia ratio is off. So you can't always assume that just because you have torque and speed that the application will be just fine. But let's cover, what is inertia? Well, inertia is, in the description here, is the difficulty in changing a rotating velocity of an object. So let's say I have a tennis ball and I throw it to you. Well, if you're not ready for it, you may look like this guy, but chances are you would be ready for this tennis ball. And the ability to catch it, as this young kid right here, the ability to catch that tennis ball and control it is that inertia mismatch of being able to grab and hold and control that tennis ball. But let's switch it up a little bit here. And let's say that I throw you a bowling ball, a 20-pound bowling ball. Well, it is going to take a ton or a lot of force to hold on and control that bowling ball because of the inertia that it generates. It's moving. So therefore, the mismatch, as we say, from load to motor is going to be significant, unless it's like a 2-pound ball, maybe. Let's take it the opposite direction. And let's say that we throw a 1-inch bead. Well, now your hand would be able to catch that bead, but you would have more inertia than the small bead. And in that case, the motor would have more inertia than the load. So it goes hand in hand with each other. So again, the inertia of a system is defined by the inertia of the load divided by the inertia of the motor. And every motor is going to have some sort of inertia. And why is this important? Well, it's important because, as we stated in the previous slide, you need to be able to maintain control of the load. The typical industry inertia ratio mismatches are anywhere from 10 to 1 and below. That's industry standard, just about saying that you don't have to do any sort of tuning per se, unless you really want to get fine in your positioning. But that is, relatively close, 10 to 1, 20 to 1, that sort of thing. There are some limitations when you move into a high inertia mismatch application, specifically either 100 to 1 or 1,000 to 1. And there are applications that are out there where you have to account for really high inertia mismatches such as this. Some things to consider. You will have to, more than likely, have a gearbox. You will have to lower the tuning gains to protect what's called as the dynamic braking circuit, as well as the accelerations and the decelerations will more than likely have to be elongated, or a longer accel and a longer decel, so that you can size accordingly. So that was mistake number 2, is ignoring inertia ratio, which is quite important. Mistake number 3 is being caught up in what's called the manufacturer crossover trap. And just yesterday, I had this call here where a gentleman wants to basically take a manufacturer's data sheet of what's currently on the machine and just, hey, what do you have that's comparable to it in Yaskawa? The main issue or the mistake here is that even though the machine is unreliable and there are obsolete parts and you may not have qualified technicians to run that particular system, it's not apples to apples when you do the crossover. So again, the easiest thing to do is to just copy and paste them. But what we find is that, again, this is a mistake. What we find is that not all servo motors are the same. In this picture here, we were showing a particular Sigma 7 series. It is the A series. It is a 100-watt motor, and you can see on the nameplate there where it's going to show you the data points of what this motor can do. Again, they're not interchangeable. There are physical size limitations, shaft sizes, the NEMA flange, the rated speeds and torques. Some motors are rated at 4,000 RPM, others are rated at 1,500 RPM, and the peaks can be changed, based on voltage. The inertia of the motor is also going to be different. So you cannot just copy one stack of parameters from one to the next. You may get close, but it won't be an apples to apples comparison. So we've talked about some mistakes. Let's look at some example servo applications that we've seen in the field. These aren't all of them. And thank you again for the poll questions that you guys answered. But some applications that we see, so rotary applications, these are used in some sort of cylinder that is rotating and maintaining a material like a slurry or a slush. You want to maintain and verify the torque that's being used. This application here would be pulling a film through a vertical form, fill, and seal machine. Another application here that is rotary is a guide arm. So in this case, this axis would be laying down a certain fiber on a particular either spindle or spool, wrapping it up, or it could be used on a large cylinder. In this application here, those fibers that we were talking about earlier would be wound onto this large spindle that's being rotated at a certain speed to maintain velocity. Some other rotary applications, this one's getting more into like the pulley style, but it is still rotary in a belt where you are sending material or products through a conveyor line that has to be going at a certain rate. Rotary applications, so this particular one, as you can see, has 4 different stations where it will index, stay, let some process go and do its thing. This application is more of a 2 spindles attached to a turret, more of like an automatic winding type of machine. Let's not forget labelers, where you are putting a label piece onto a product. And finally, let's look at this rotary knife application, which is quite huge, but there are a ton of these applications out there where it is using servo motors. So with those that you've seen so far, let's talk about some other mechanisms, and let's start to ask some of the questions that we typically ask, because going back to basics is always a good thing, just to make sure that we have everything from the ground up correctly sized. So in this case, we've got a gantry style application where it is using a ball screw. The questions that you want to start asking are, what is the load of the mechanism that you're moving? If you don't know, you can do some guesstimations. Typical things that we see here, of course, 1 inch is 25.4 millimeters, and the density of steel, as a good friend told me, is 7.86 grams per centimeters cubed. So you can use that to roughly get an estimate on what something weighs. The orientation is important. Is this a horizontal axis or is it a vertical axis? Do you have some sort of an incline that you have to overcome? The next question that you would ask is, what is the speed? And typically, we want to find out what the worst case speed is going to be. And it should be in either actual units or in estimated units. Can't be, it's got to go real fast or it's got to go real slow, because that's all relative and you can't really do any sizing with that. If we switch it up here, let's take a look at the rack and pinion, which is a gantry system. That the next question you want to ask is, how far does this axis have to travel? And again, actual units work better because you can do real sizing with those actual units, not just this much or this far. It's got to be some units to be putting on there. What's the precision that's required for this particular axis? Some applications, a 1/4 of an inch or 1/2 an inch is perfectly fine. If you're moving around drums or washing machines or dryers, that sort of thing, doing pick and place, 1/2 inch is just fine. But some other applications need to be within thousandths of an inch. So it's a good question to ask about what precision is required. The environment is also another question that you should know. What environment is this machine going to reside? Is it going to be outdoor or is it going to be indoor? Or is it sometimes going to be in a cold environment like a freezer and then move into more of an ambient or a warm environment back into cold? In that case, you have to account for that. What is the duty cycle? So how often does this machine have to run? Is it a 24/7 operation or is it 2 shifts and it kind of just parks itself for a little while? Moving on to a different application is the vertical form, fill, and seal machine. Again, these questions that you want to ask are pretty typical from what we've laid out in the previous slides, but what is the load? In this case, it would be a tension. So piecing these 2 pulleys together with a belt is going to be pulling this material down. The orientation for this would be a vertical application. The speed, what speeds are you trying to maintain? In this case, we know that the flow or the webmaster needs to be running at 330 feet per minute. It's good to always do the conversions. I like to do things in inches per second, but if you can follow with the feet per minute, that's fine as well. The travel, how far does it have to move? In this case, we knew that it's got to be a 4-inch move. Continuing on with the same questions as before, or what's the required precision? Is the environment, what environment is this machine going to be in? This one in particular was an indoor food facility. And then what is the duty cycle? This application, I think, was running 2 shifts, so 2 8-hour shifts is what they were looking at running for that. The interesting thing is we move on to what we used for this particular application was actually an older version of the Sigma series, but it falls in line with the Sigma 7 series J versions. These are lower capacity applications. The power ratings with this are going to be between 50 watts up to 1.5 kilowatts. It is what's called the medium inertia application, medium inertia servo motor, excuse me. The rated speeds are going to be at 3,000 RPM, and you've got different rated torques that are going to go all the way up to 4.7 Newton meters. So that was actually what was used. I went back to look at the model for that, and this would be the closest one that it was used for that machine. If we move on to the back of this vertical form, fill, and seal machine, in order to size it correctly, we ask the same questions. What is the load? What's the orientation? what is the speed? And please make note that sometimes you do have to account for the gearing ratio. So there's a pulley, there's a driven pulley, or the driver pulley rather, from where the motor would be connected, to the driven pulley, which is usually the one that is kind of slave to the main one. What travel? So we know how far this machine or this particular axis has to run. What is the required precision? And of course, the environment, well, it's the same machine that was going to be put into an indoor food facility. And then the duty cycle falls in line with the others. If you have a 5 or an 8-axis system, generally those last 3 are going to be the same. But it's good to know if one axis has to be better than all the rest because of the different operations that are being done throughout the machine. Switching on over to plasma cutters. These 5-axis systems are pretty cool and pretty neat. Typically, they have what's called the X and the X prime axis. Heard it called different things, XA and XB, X1, X2, 1 and 2. But more than likely, you will have 2 servo motors on both sides helping for the gantry that's coming up here, this Y-axis, which could also be called the bridge. But same sort of questions that you would ask throughout all these axes are the same ones we just covered before. But the Z-axis, which would be going up and down. Some of these applications do have what's known as the bevel axis, which swivels the plasma torch in the front there. Interestingly enough, for this application, this series is using the Sigma 7A series, and these are known as the general purpose workhorse servo motors. The power ratings with these go from 50 watts all the way up to the 7 kilowatts, so higher than the J series, which was stuck at the 1.5 kilowatts. These ones go all the way up to 7 kilowatts. The A series are going to have less inertia than the J. Why do I make that point? Depending on the application, and if it's some sort of contouring, you may find that the J series and the A series will do the same application. So which do you choose? In that case, you'd go back to, well, let's back up. You could say, well, what's in stock? What is maybe lower investment price for that particular servo motor? But in any case, look at the application and know with the J series, it's going to take less inertia to move. So it's going to be less current to move that motor. If you're contouring and that sort of thing, maybe that's what you need. For the A series, though, it will take less inertia to move than the J series. So some things to note there. So rated torques, these ones go up to 22.3 Newton meters. And then you've got some rated speeds on these that go to 3,000 RPM. One that I didn't touch on was the Sigma 7G series. Now, these motors are going to be shorter and squattier. They're really good servo motors. They provide a compact footprint, so they are that smaller type. They're really compact. They have higher torque than the J's and the A's series of servo motors. These rated torques go up to 95 Newton meters, but the caveat is that the rated speeds are cut in half. So you're not going to get you're not going to get like 6,000 RPM peak speed out of these motors. The peak speed out of these motors would be 3,000 RPM, but the rated, where the knee is going to be at the 1,500 RPM. Moving on to large presses, this is an application where it was doing two processes here. One was doing indexing where the process is on the left-hand side, and then shooting out that sheet of metal out to a different process on the other. Another series of servo motors that we could use is called the direct drive servo motors. These are newer, so what it's going to do, it saves space and it eliminates backlash. So you don't have to use a gearbox in this case. They provide for much higher inertia ratios than the regular rotary servo motors. It cuts component cost. It does give you that extra mechanical strength because it's directly bolted to a really large inertia load. But the caveat is these do require a higher initial investment than a regular servo motor. So what are these? Well, these are the Sigma 7D style. This D style of direct drive is going to be used for low-speed applications that are above 14 newton meters. They're for higher inertial loads. It's a large hollow bore. In this case, the outer rotor actually is what rotates. So it is an iron core, but the outer rotor of this motor is what rotates. Contrast that to the 7F series motor. These applications are for high speed that are below 14 newton meters. They are going to be for their lower inertial loads. It's compact just like the other one was, but this case, the inner rotor is what rotates. And the maximum speeds that these guys run are going to be at 600 RPM. Hey, who doesn't like good hand sketches? But designs are also a good thing to have when you're discussing or talking about sizing, because let's face it, a pen and paper is just always going to be great to do, because you can do your calculations, you can write out what's needed for the particular application as a visual, and I'm very visual. Okay, let's switch on over to the importance of gearbox selecting. So let's talk about, why is a gearbox necessary? Well, in this case, gearboxes do three things. They really decrease the output speed at the load, they will increase the output torque, and they're going to be able to reduce the motor size. So why is that important? Well, if you reduce the motor size, then you don't need such a large motor to move the load. You can make use of the gearbox, the mechanical advantage that it provides. Yaskawa does have what's called the Sigma 7 series gear motors, and we'll touch on a couple of these in a couple of slides. But essentially, you need to know that not every application needs or requires a gearbox. But when it's necessary, it will reduce the reflected inertia of the motor by the square of the ratio. So if you have a 2-to-1 gearbox ratio, then it will reduce the inertia back to the motor to the fourth power. So 2 to the fourth power, 2 to the second power, which will give you 4. If it's a 5-to-1, it would be 25. So the rule of thumb is you generally want to stay within the 10-to-1 inertia ratio. Yaskawa's algorithms do a lot for up to 40-to-1 inertia mismatches on the Sigma 7. A single stage reduction is usually where you want to maintain that. The reason for the 10-to-1 ratio is that you will stay within a single stage reduction versus having to go to a 2-stage, which would be more of an investment on the gearbox. So try to stay below the 10-to-1. Also, the cost, you have to look at the cost between the servo motor and the gearbox to determine which one would be the best one. We touched on some of the gear motors, but here's our lineup that we have for the Sigma 7 series, and you'll notice that it follows suit with the actual motor series as well. So the Sigma 7J, the Sigma 7A, and the Sigma 7G. These are all factory installed back of the motor. They provide high precision operation, high torque capabilities. They are in our technical supplement for all the data and the specs that what they provide. The backlash is less than 5 arc minutes, and we do have gear ratios ranging from 3-to-1 all the way up to 50-to-1. So if your application needs it, we should have something that you can use for the sizing. So now I'd like to turn our attention to the navigation portion of where you can find more data and some video links. So if you go to yaskawa.com and you hover over support and training and the e-learning curriculum, you'll be directed to what's known as the Servo in Motion tab there. Hover over that and click, and then go to Servo in Motion e-learning. So there's a lot more in-depth training in our e-learning curriculum that you can use for sizing. Click down onto the subtopic in sizing, and then you'll find the various different videos to go over some of the applications that we've touched on here. Also, to find our sizing software, you can hover over Products, Motion, and Sigma 7 Software Tools. You will find what the name of our software is called is Sigma Select. You download that. It's at no cost at all, and you can use it to start sizing. So some other motion sizing links that we have. We are on LinkedIn, so find us on LinkedIn, follow us. We'd love to have you there. There is the Twitter. We are also on Twitter. And hey, let's get ready. If you can smash that like button on YouTube, we would appreciate it. Our subscribers are continuing to increase as we speak here. So now it brings us to the point of some live demonstration, and I think what I will do is show our application that we will size together, going to give you an in-depth glimpse of what the sizing software can do. And what we will be looking at here is the rotary knife application. So if we have some of the stats here for the rotary knife is that, we're typically you start asking the same questions about what you're moving. What is the data that you want to use? So if we go back to the rotary knife application that we showed earlier, we're not going to do a really huge one, but in this case, we did I did a rotary knife application here about 6 months ago, and it was using a 2.75 inch OD, and it was 40 inches in length. So that's what we'll go with for now. We will look at, so the payload is going to be the density of that rotary knife, because that's what we're rotating. The orientation is going to be horizontal. Our speeds, we want to maintain 255 cycles per minute. The distance, of course, is we're making 360 degrees or 1 rev. The environment for this rotary knife is going to be indoor, and we know that the duty cycle is going to be 85%. The specs, as we already went through, is it's an OD or an outer diameter of 2.75 inches. The material is going to be all steel, and the length of this guy is going to be 40 inches. So bear with me just 1 second here, and what we will do is start to go through this sizing together. So if we go back to this here, give me a second. And I believe that should be coming through. All right. So our Sigma Select software is here. It's free. It's at no cost. You can download there. I do recommend when you open up this software, please give it a project title. We will say rotary knife here. And you do want to save this file right away. So we'll do a save as, find a location, just put something in here in the desktop, and we'll say rotary knife. Okay, so at least that's saved. Onward to the next tab, which is called the load editor. Now, you'll notice that there are quite a few different mechanisms in here. If you want to look at a drop-down, we can look at the drop-down here to change that mechanism. But what we want to look at and focus is going to be on the rotation table. So to get the rotation, the rotating inertia, we'll go and click on this inertia calculator button, which will pull up a small window here. Then the component, you can change the name to rotary knife or anything that you want to label it as. And we're going to go with inches for all of the dimensions here. So we did say that this is going to be a 40-inch cylinder. The outer diameter was 2.75 inches. There's no offset. And the user spec, we have some of the densities in here. In this case, we'll probably use the carbon tool steel. You could use the other stainless steel as well, but we'll just stick with carbon tool for now. It will generate what's the total inertia of the load, as well as give you the mass. And you can click accept. That will give us the rotating inertia. There's no external torque in this case. The friction coefficient, maybe we can look at the mechanism as using ball bearings, so we'll give it a small coefficient of friction. When I size, I generally do not put a gear ratio in here just to see what is the largest motor I'm going to use for this application. So we'll move forward to the profile editor. Now, we did say that the application needed to maintain 255 cycles per minute. So if we look at 255 cycles per minute, we divide that by 60, we get 4.2, and you want to take the reciprocal of that. So that'll get you how much time you have for one revolution, which is going to be 235-ish milliseconds. So we will go in here and we will say, give it trapezoid. At the bottom left-hand corner, we'll give it that 0.235 milliseconds. And I like to change this to revs. So we will say, well, 1 rev has to do that application there. So there's our profile from start to finish. So XL, decel, we'll go the 1 rev. But this trapezoid is pretty, how should I say, pretty aggressive in the sense of how we're going to be making this move. It'd be nice to know if we can add some sort of an S-curve into this profile. To do that, we will switch this down here to percent of XL and decel. Watch what happens. You see how right now we're at 0. It's a straight line from the XL all the way up to the traverse. But if we say 50%, we want to use 50% of that acceleration and deceleration, you see that the motion profile actually has a nice slight curve to it called an S-curve. This will benefit the machine in the long run because of the life cycle of the machine as well. So let's move forward to the motor results, and a lot of data here, right? Huge list. So let's say we don't want to use the Sigma 5, which is the previous series of motor. And again, we just want to look at what's the worst case scenario of the motor that we can use. Let's take away the gear motors as well. We know, which is another question you should ask, is what's the voltage? We know that we want to stick with 200 volt for the power. And we don't know the motors just yet. But now you can see that this list is now condensed into the ones that will work for this application. It's important to note that on the right-hand side here, you've got some non-stock items. I probably wouldn't pick those. So we can look at this Sigma 7A series motor. It is a 3 kilowatt, 200 volt motor. Hey, torque and speed are good, right? Let's look all the way to the right, though. The application inertia, as compared to the motor, is actually showing a 26.5 to 1. In this case, the column for allowable inertia is at 5 to 1. So we want to stick with something that gets us 5 to 1 and below. This goes back to mistake number 2, I think it was. So the inertia ratio is something to take into account. Even if we move forward with this and look at the motor details, you can see that right here we're not really using a lot of the RMS torque of this motor, and the speed for that matter. Actually, we're not using a lot of the speed for this. We are using the torque. But again, we are 1-to-1 matched up from servo motor to the rotary knife. Let's look at what a gear motor would give us. We can see also that the required rated speed, actually the peak speed for this motor, is at 383 revs per minute. So we've got a lot of headroom. For this particular motor, we've got up to 6,000 RPM. And the required rated speed is at 239. So if we went in and added at least a 10-to-1 gearbox, we could see what this is going to do. And for this, I will go ahead and select the motor series, which is going to be the A series. And when we look at the differences here, we can see that the A series, if we use a 400 watt motor with a 10-to-1 gearbox, we can do this same application as compared to a 3 kilowatt motor directly coupled to the load. So thereby going from a 3 kilowatt all the way down to a 400 watt motor with a 10-to-1 gearbox, we can see the differences of the speeds and torques. Here is showing the 400 watt with a 10-to-1 gearbox, or the 10-to-1 gear motor, as opposed to a direct drive 3 kilowatt motor. So the sizing software is able to do the investment comparison. One thing I didn't touch on is going back to the motor results. The very far right is what's called the cost factor. So if you see a 1, then you know this is the base. Like this is the what servo motor can do this application. Anything else above the 1 from there is basically a percentage. From the 1 up top, you can see that the bottom here is about a 27% adder to go with a direct drive. But even when you go with the direct drive, your inertia ratio is off. Continuing on, or wrapping up rather, for the motor details, you can then move on into the different tab to show if there's any regeneration that is required as far as the regen resistor, or going back to the servo pack as well. At this point, you can save, and then you can create what's called the PDF. And what this will do is it'll create a nice list of everything that we entered here. We could put in all of our notes and company, customer, but it will generate this really nice, beautiful looking sizing summary where it tells you all the torques that you need, any of the mechanical information, the move profile that was used to calculate, and finally, the data that's used for the motor for that particular application. So at this point, I will minimize, and I need to stop showing my screen. Let's go back here. So wrapping up, what we've covered today is some of the common mistakes. Again, mistaking the AC induction servo motor, the AC induction motor with the servo motor, ignoring inertia ratio, the getting caught up in the manufacturer crossover trap. So those are the main common mistakes that we covered today. The example servo applications, we reviewed some of those that we've seen there. And also we looked at the gearbox selecting and the importance of when to use a gearbox, followed by our live demonstration. With all of this, we know, I mean, it can get complex on a couple of things. So who do you call for help? In this case, you could reach out to your local distribution or your local integrator for an in-depth, local call where they can come out and start to ask these same type of questions for your specific application. Our number is 1-800-YASKAWA. We love to help in sizing as well. We are remote, and our website, of course, is yaskawa.com. And with all that, again, my name is Sixto Morales. I lead up the Southwest territory for the engineering team, as well as Latin Sales America. And we thank you very much for your time. And I think at this point, we will switch on over and have some Q&A.
Thank you, Sixto. Now we'll have a question and answer session with the audience, and you'll have an opportunity to provide some more learning for us. Type your questions for Sixto in the Ask a Question box on your screen, and we'll get to as many as time allows. Questions that we don't get to today will be posted online with the archived version of the webcast. Remember to download a certificate of completion and a copy of the presentation by using the Event Resources tab on the left side of the screen. All right, now we'll go on to the Q&A. So what is how are our servo motor speed ratings related to sizing?
Speed ratings related to sizing, so the speed will determine how fast the motor needs to run in order to move the particular application. If you go higher than the rated, that's getting into what's called the peak region or the intermittent region. Yaskawa servo motors actually allow for 3.5 times the amount of torque that's required for an application to get into the intermittent, but it's only for about 3 seconds or so to come back down below the rated or the rated speed of the motor. So in that case, you want to stay below the knee of the servo motor's speed rating.
Good. Thanks. Moving on. Let's see. What is a typical encoder resolution for a servo motor, and does that affect the sizing at all?
Typical encoder resolutions, they vary from different manufacturer. Yaskawa's resolution is 24-bit resolution, so it's over 16 million pulses. Our previous generation was a Sigma 5 version, which was a 20-bit, which was just over 1 million pulses as well. But there are others that are lower. I'm pretty sure there's some that are higher, but I know that there are others that are lower. And that can, that affects the sizing because of the precision and the resolution of the data coming back to the amplifier or the servo pack. And that's used for the algorithms, specifically in Yaskawa's servo pack, that's used for the algorithms for things like vibration suppression, auto tuning, notch filtering, that sort of thing.
Great. In terms of inertia, how does a servo amplifier account for inertia mismatches, and how high can they be?
Oh, so yeah, we touched on a little bit of that as far as accounting for inertia mismatches. Our sizing software does a real good job of highlighting where that number should be, in particular for the servo pack. But again, using higher inertia mismatches are going to result in lower accelerations and decelerations. The tuning gains will also have to come down a bit because you don't want to send more energy back into what's called the dynamic braking circuit for the servo pack to do any sort of damage. But yeah, they go hand in hand as far as, and also using a gearbox to reduce that inertia.
Great. Keep those questions coming as we go through the Q&A session with Sixto. Go ahead and type the questions in the Ask a Question box, and we'll get to as many as we can. Here's another one. Why choose a trap profile over triangular?
The trap profile will allow you to be able to cut it into thirds, accel, traverse, and the decel. The triangular you could use, it's really going to be cut in half. It's just an acceleration going up and a deceleration going down. Sometimes you would want to see you're going to be maintaining a certain speed for a while. So they vary as far as the different profiles that you want to choose. But in any case, I always resort to just the trapezoid profile so that we can look at accels and decels in a more clearer manner, if you will. But you can definitely use a triangular profile as well.
Good. Duty cycle was always based on a short period of time, which is the time that is required for the motor to get to a steady state temperature. So would it be something like 80% of 10 minutes? Is that true? Or is it how long will it run in an 8-hour shift?
Yeah, so duty cycle can be compared to more of the in order to do, we can get it even smaller, to do a full cycle, the time that it's on versus the time that it's off. Let's say that it's running, it's doing its trapezoid profile, and then it's dwelling for a while. So that could also constitute as a duty cycle. But over the length of time, let's say that it's only running 8 hours out of a 24-hour shift, then you know that there's going to be some cool down time for the motor. But within even the cycle itself, there will be a period where the dwell lets the motor cool off a bit before it has to be excited to do the application.
Great, thanks. In terms of inertia, how does a servo amplifier account for inertia? We did that one. Okay, great.
I think we did that one.
Yeah. How do some applications for servo motors result in more of certain sizing errors than others? In other words, so in certain applications, do you see more instances of errors that you described?
Yeah, actually touching on this about a week ago, yeah, we had an application where they wanted to kind of do a trial and error. This motor was using a 1 kilowatt, so we should just switch over and use that same style of that same wattage or the kilowatt wattage for the application. And it turned out that it needed a lot less, and so the motor was oversized in that case. And when we asked the questions about what sizing was done with this, the answer was, well, there wasn't. This is what was used before, so we just crossed it over. So going through those questions again, and we were able to actually pinpoint and show, you could get by with a 200-watt motor, which is unbelievable, using a gearbox versus sticking with a 1 kilowatt motor. And in today's times about supply chain and so forth, that 200-watt was in stock and was able to to help them as well. So it does definitely need to go through a sizing.
That flexibility helps in these supply chain times, I'm sure.
Yeah, that's right.
Is the backlash figure related to the encoder resolution or to something else?
The backlash is related, yes, to the encoder resolution. So those motors actually have, I forget, I think it's either a 24-bit encoder resolution on those direct drives or 20. But yes, so that's going to be related to the resolution of the feedback for that particular series as well, and how tight we can get those motors.
Good. So in the examples, when you discuss speed, is that always the motor speed, or are you talking about load speed?
In the examples showing this, well, so it depends. If you're talking like feet per minute, those would be what the, like for the vertical form fill and seal machine, that is the actual material flowing that it needs to run at. So therefore, the motor would have to account based off of the mechanical and the pulleys and the dimensions and so forth, would need to account to maintain that speed as well, or faster, but it's got to at least maintain those speeds. If we're talking, RPM, then we're looking at either the rated or the peak speeds of the motor themselves as far as they can go.
Good. What happens if the regeneration is called for, but we don't use resistors?
Well, our servo packs, the Yaskawa servo packs, will generate an alarm, and it will highlight definitely that a regen resistor is required. And really what that is, it's basically the load acting as a generator back into the motor. That energy has to be dissipated somewhere. Internally to the servo pack, though, there is a built-in limit. So let's call it 40 watts or 80 watts of regen that's allowed. Any regen that goes above that will trigger an alarm, and therefore a proper sizing should result in knowing what the regen value is, and therefore using what's called an external regen resistor, so that it bleeds off the energy to the external resistor.
Well, and that certainly helps with the overall energy efficiency of the application too, depending on what you're looking at.
That's correct. That is correct. Yes, it can.
So you suggested a gearbox could result in a lower cost servo motor than a direct drive design for some applications. Over the life cycle of such applications, would the energy savings overtake the capital cost savings?
Over the life cycle of such applications, would the energy savings overtake capital cost savings? I would have to say yes, because you're able to use a smaller motor in the case of, instead of using a 3 kilowatt motor, you could use a 400 watt motor, which will reduce the amount of energy that's needed for that application. So there would definitely be some energy savings going on for the various applications.
Great. Are Yaskawa servo motors only compatible with Yaskawa drives and control systems, or is there some flexibility there?
So we match perfectly, like 1-to-1 from the servo pack to our servo motors. So in that case, the servo motor will go with a particular amplifier from Yaskawa. And that's really because in our catalog and our technical supplement, all of the data points that we have there are verified and guaranteed to perform up to those specs. Using a different manufacturer's amplifier, we can't guarantee the same specs, the same ratings as we can within our catalog.
Good. Perhaps time for one more, but the audience can keep submitting questions, and we'll get to those offline afterward. Does Yaskawa have smart motor offerings?
Does Yaskawa have smart motor offerings? Is there a little more to that?
Yeah, that was it.
Smart motor offerings. What I can say, I don't know if this exactly is the question, but when you do plug in, so there's going to be a power cable and encoder cable. When you do plug in the encoder cable into the amplifier is going to know automatically which motor's connected, what encoder parameters are, the model, the serial numbers, the part numbers, and that sort of thing. So by smart, I wonder if it's like a plug and play type thing. Yes.
Or maybe integrated motor drive.
Integrated motor drive, at this time, no. However, we do have a motion controller that is embedded into an amplifier. So it looks like you get just an amplifier, but there is an actual motion controller embedded in there that you can use as well with the servo motor.
Great. Thanks, audience, for the great questions. And thanks again to our great speaker, Sixto Morales, for sharing his time and his expertise, and especially his deft to answering the questions at the end here. I'd also like to extend a special thanks to our sponsor, Yaskawa, for today's event. And now that we're just about done, we do want to hear how we did. The survey will pop up on your screen as soon as the webcast ends. Please take a moment to complete it because we use the information to improve our webcasts. Finally, on behalf of Control Engineering in Yaskawa, I'd like to thank you for attending. This concludes our webcast. Thank you and goodbye.